I welcome you all in the fifth lecture on psychrometry. In the previous lectures, we talked about various psychrometric properties and also derived the relations for them. And in the last lecture, we also solved some numerical problems on the psychrometric properties. The properties of atmospheric air can be represented in tables or graphical form. The graphical form is called the psychrometric chart. It is universally used because it presents a great deal of information very simply, and it is also helpful in studying air conditioning processes. The purpose of any air conditioning equipment is to change the condition of the entering air to a new condition. This change is called a process. Showing these processes on the psychrometric chart is very helpful in selecting equipment and in analyzing various problems. Processes are shown by drawing a line from the initial air condition to its final condition. The air changes its properties along this line. Most processes are represented by straight lines. A psychrometric chart is shown in figure 2. There are slight differences in the arrangement of charts furnished by different organizations. This should be studied. Any condition of air is represented by a point on the psychrometric chart. The condition can be located once two independent properties are known. Because each property is represented by a line, the intersection of the two lines establishes the point representing the condition of the air. Once the condition is located, any other property can be read from the chart. Psychrometric chart provides a picture of the way in which the state of moisture alters as an air conditioning process takes place or a physical change occurs. Familiarity with the psychrometric chart is essential for a proper understanding of air conditioning. Any point on the chart is termed a state point, the location of which at a given barometric pressure is fixed by any two of the psychrometric properties. It is necessary and convenient to design charts at a constant barometric pressure because barometric pressure does not alter greatly over much of the inhabited surface of the earth. When the barometric pressure is significantly different from the standard adopted for the chart or the psychrometric tables to hand, then the required properties can be calculated using the property equations. The British standard is that adopted by the Chartered Institution of Building Services Engineers for their tables of psychrometric data and for their psychrometric chart. It is 101.325 kilopascal. The American standard is also 101.325 kilopascal, and this value is used by the American Society of Heating, Refrigeration and Air Conditioning Engineers. The chart which is most commonly used is the omega T chart, that is specific humidity versus dry bulb temperature chart. So in this particular chart, that is in figure number 2, you would notice that along the abscissa or x-axis we have taken the dry bulb temperature in degrees Celsius, and along this ordinate or y-axis we have taken the moisture content or the specific humidity. This chart is normally constructed for a standard atmospheric pressure of 760 mm of Hg or 1.01325 bar, corresponding to the pressure at the mean sea level. So in this particular psychrometric chart, you would notice different lines for different psychrometric properties. This particular line is for relative humidity equal to 100%. So this is basically the saturation curve on the psychrometric chart. You would also notice that there are horizontal lines for constant specific humidity and there are vertical lines for constant dry bulb temperature. There are inclined lines also like this for constant specific volumes and slightly more inclined lines for constant wet bulb temperature lines. So these constant wet bulb temperature lines, they originate from this saturation curve and then move inside of it. You would also notice a enthalpy scale on this psychrometric chart. So this scale basically gives us the value of specific enthalpy on the saturation curve only. There are curved lines also. These are the enthalpy deviation lines, because this enthalpy scale reads the value of the enthalpy when the air is saturated. So in order to determine the enthalpy of any other state of unsaturated moist air, we need to go along this constant WBT line and find out the how much enthalpy deviation is there, and accordingly we can determine the enthalpy of unsaturated moist air. Uh, we will discover one by one how these property lines are psychrometric property lines are developed on the psychrometric chart, and how this particular chart is helpful in determining other psychrometric properties if at least two of the psychrometric properties are known to us. This particular psychrometric chart is for the normal drivable temperature range of -10 to 55 degrees Celsius, and a specific humidity range of 0 to 0.033 kg per kg of dry air. Psychrometric charts are also prepared for sub-zero temperatures for extreme winter heating calculations, and for high temperatures for calculations of drying processes. In a sub-zero temperature chart, the water vapor pressure is that of sublimated vapor over the ice, since 0.01 degree Celsius is the triple point of water. Also, the latent heat used for enthalpy calculations is that of sublimation instead of vaporization. Psychrometric charts are to be specially constructed for localities at higher altitudes and consequently lower barometric pressures. A keen observation of the psychrometric chart is really essential in order to understand the range of various psychrometric properties on the psychrometric chart. As we discussed earlier, that the dry bulb temperature here is taken along the abscissa, and it is ranging from usually 0 to 55 degrees Celsius, and along the ordinate we have taken the specific humidity or the moisture content, and it ranges from 0.0 to 0.033 kg of water vapor per kg of dry air. There are lines, so this is the saturation curve, and there are lines parallel to these. So these are the constant relative humidity lines, and they usually range from 10% to 100%. There are inclined lines of constant specific volume also. So when we look at its range, it ranges from 0.75 meter cube per kg of dry air to 0.95 kg. So this is basically the workable range that most of the air conditioning equipments that we are encountered with, they usually operate in this particular range. A specific enthalpy scale is also given here, which ranges from this 0 to 115, and up to this 145 kilojoules per kg of dry air value. There are constant WBT lines also. These lines are slightly more inclined as compared to the constant specific volume lines. So their value can be read from this saturation curve here. So as we move along this, we go through the different wet bulb temperature values at saturation. So these are 0, 1, 2, 3, 4, 5 degrees Celsius like this. There is also a very important scale given onto the right of this constant specific humidity scale, that is a sensible heat factor scale. This is very important in locating or in generating the room sensible heat factor line on this psychrometric chart that we shall discuss later. And also a very important point is marked on this psychrometric chart. This is known as the alignment circle. So usually in most of the charts, in most of the psychrometric chart, it appears at 25 degrees Celsius dBT and at 50% relative humidity. So intersection of this constant relative humidity line of 50% and a constant dry bulb temperature of 25 degrees Celsius. So it lies at the intersection of these two lines. In some other charts, you may find that the location of this alignment circle is slightly different from this. It may appear at 24 degrees Celsius and 50% relative humidity also. So let us have a look of the range of various psychrometric parameters that appear on the psychrometric chart. we notice that the dry bulb temperature ranges from 0 to 55 degrees Celsius. Wet bulb temperature ranges also from that 0 to 55 degrees Celsius, and dew point temperature, it also ranges from 0 to 55 degrees Celsius. Specific humidity ranges from 0.001 kg of water vapor per kg of dry air to 0.033 kg of water vapor per kg of dry air. Specific volume ranges from 0.75 to 0.95 meter cube per kg of dry air. Relative humidity ranges from 10 to 100%, and specific enthalpy scale goes from 0 to 145 kilojoules per kg of dry air. There are various types of psychrometric charts available with us. For normal dry bulb temperature range of 0 to 55 degrees Celsius and omega, specific humidity ranging from 0 to 0.03 kg per kg of dry air. For sub-zero temperatures, that is for the case of the extreme winter heating, we have got a separate psychrometric chart. Likewise, for drying processes which involve the high temperatures, we also have a separate psychrometric chart. And for localities at higher altitudes where the barometric pressure is lower, for this purpose we do have one more psychrometric chart. This particular table just gives us an idea of how the barometric pressure varies with the, that is, height from the mean sea level. So obviously when we move up, that is, go above from that mean sea level, the barometric pressure decreases. I hope that you guys still remember that when a given sample of the moist air is cooled at constant pressure, so the thermodynamic state of the water vapor changes along this constant pressure line, and the temperature at which the moisture which is present in the moist air becomes saturated is known as the dew point temperature. So there are two ways of making the air saturated. First, if the given sample of the moist air is cooled at constant pressure, eventually it reaches a dew point temperature where the moisture becomes saturated. Second way of making the air saturated at its dry bulb temperature is that if we keep on injecting the moisture into it, so the thermodynamic state would change along this isothermal line. So suppose here we have got a point number 1. Point number 1 reflects the thermodynamic state of the moisture which is present in the unsaturated moist air. If I just move along this horizontal path and continue to inject moisture into the air becomes saturated, means it is now holding the maximum amount of moisture at its own dry bulb temperature. So air is said to be saturated in this condition because the water vapor which is associated with the dry air part is now saturated. Its thermodynamic state lies on this saturated vapor line. So the saturation line represents the states of saturated air at different temperatures. As an example of fixing such a state on the psychrometric chart, consider an atmosphere A at 20 degrees Celsius dry bulb temperature and saturation as shown in figure 1. So we are assuming that the initial state of the air given to us, that is the moist air given to us, is saturated. We understand here that when the given sample of the air is initially saturated, it's all three temperatures, the dry bulb temperature, wet bulb temperature and dew point temperature, they become equal, they are same. So since the given sample of the air is saturated, so we will directly move on to the steam table, and at 20 degrees Celsius we will look for the that is the saturation pressure at a temperature of 20 degrees Celsius, because at 20 degrees Celsius the air is saturated. So corresponding to this saturation temperature of 20 degrees Celsius, we will notify the value of the saturation pressure. So it comes out to be 2342 Newton per meter square. So this is nothing but the partial pressure of the water vapor as well as the saturation pressure at 20 degrees Celsius. So PS is equal to PV, because definitely when the given sample of the moist air is saturated, its relative humidity is 100%. So phi relative humidity is nothing but PV upon PS. So these two partial pressures are going to be same. Partial pressure of the water vapor becomes equal to the saturation pressure at that particular temperature. So with the help of this steam table, we could note down the value of this PS, which happens to be equal to PV, and this is equal to 2342 Newton per meter square. Because this particular table is of some different authors, so you might notice certain difference in the values of this saturation pressure and the temperatures. So here it is 2337, whereas it is 2342 in as per the text, Newton per meter square. So having determined this partial pressure of water vapor or saturation pressure, we will go for calculating the partial pressure of the dry air. So it is going to be the total pressure, the barometric pressure minus the partial pressure of the water vapor. So we know that the total pressure of the barometric pressure is nothing but that is 101,325 Newton per meter square or Pascal minus 2342, that is PV. So that gives us a value of the partial pressure of the dry air at as 98983 Newton per meter square. Now at this 20 degrees Celsius, we will determine the specific humidity. So when the given sample of the air is at saturation state. So omega, the expression for this specific humidity is 0.622 PV upon PA. So we will simply insert the value of PV and PA calculated here in this expression for the saturated specific humidity. So when we do so, the value comes out to be 0.01472 kg of water vapor per kg of dry air. So now we are having the two parameters with us, that is the two psychrometric properties with us. One is the dry bulb temperature and the second is the specific humidity. So we know that on this omega versus T psychrometric chart, omega is taken along the ordinate, that is along the y-axis, and temperature is taken along the abscissa. Dry bulb temperature is taken along the abscissa. So starting from some reference value of 0 degrees Celsius, we will keep on marking the temperature. The moment we achieve 20 degrees Celsius, we will draw a vertical line from here for constant dry bulb temperature of 20 degrees Celsius, and also from this origin point, it is at this particular location omega is 0. So we will also suitably scale it down and mark the graduations for different values of the specific humidity. Suppose at this particular point we have got a specific humidity of 0.01472. So what we will do now, we will draw one vertical line for constant dry bulb temperature of 20 degrees Celsius, and we will also draw one horizontal line for a specific humidity of 0.01472 kg of water vapor per kg of dry air at saturation. So intersection of these two psychrometric properties, that is the dBT of 20 degrees Celsius and omega s of this much value, will ultimately give us a point number A. So this is nothing but the saturation state of air at 20 degrees Celsius. Likewise, we will keep on determining the saturation, that is the specific humidity at different temperatures, and we will continue to mark. Suppose now we need to determine the that is the how much is the specific humidity when the air is saturated at 25 degrees Celsius. So what we will do next here is we will directly move on to the saturation temperature of 25 degrees Celsius and look at the value of the saturation pressure. So this new value of the saturation pressure is nothing but the PS or PV. We will again determine the partial pressure of the dry air and again will calculate the specific humidity at 25 degrees Celsius saturation. So again the intersection of one vertical line drawn from this 25 degrees Celsius dry bulb temperature line and one horizontal line for new, that is the increased value of the specific humidity, will ultimately give you one more saturation state, and that is the process of generating this saturation curve on the psychrometric chart. So we will continue to plot different saturation states at different dry bulb temperatures. So ultimately it is locus of various saturation states which are obtained by the intersection of different dBT lines and different omega values. Now we shall learn how the constant relative humidity lines are developed on the psychrometric chart. I hope that all of you must be remembering that the relative humidity is the ratio of the actual vapor pressure to the vapor pressure which would exist in a saturated mixture at the temperature of the air. The saturation line on the chart, on the psychrometric chart, is therefore the line for 100% relative humidity, since for all points on this line, the partial pressure of the water vapor is equal to the saturation pressure at that particular temperature. So the lines on this chart for any other desired value of the relative humidity can be constructed as follows. So how did we locate the point number A on the psychrometric chart? It was obtained at a dry bulb temperature of 20 degrees Celsius. So for the purpose, we drew one vertical line for constant dry bulb temperature at 20 degrees Celsius, and also one horizontal line for the specific humidity at saturation state. So that is how we obtained the intersection of these two property lines and ultimately had this saturation state. Now suppose if we wish to generate a line for constant relative humidity of 50%. So obviously the partial pressure of the water vapor is going to be half of the value which is at 100% relative humidity at the same dry bulb temperature. So earlier we had the partial pressure of the water vapor. If you still remember, that partial pressure of the water vapor was, at saturation, it was 2342 Newton per meter square. So definitely at point number C is that is we are trying to generate a line for relative humidity of 50%. So partial pressure corresponding to the point number C is obviously going to be half of this value. So it is going to be 1171 Newton per meter square. So this is going to be the partial pressure of the water vapor. Obviously, when the relative humidity is lesser than 100%, so air is not saturated, it is unsaturated moist air. So at this particular point, so PB is known to us. We will simply go for determining the partial pressure of the dry air now. So subtracting this 1171 from the total barometric pressure of 101325 Newton per meter square, so that will give us a value of the partial pressure of the dry air 100154 Newton per meter square. So with the help of the formula for specific humidity, omega equal to 0.622 PV upon PA, we will simply insert these two values here and will ultimately come to know the value of the specific humidity corresponding to the point number C. So when at 20 degrees Celsius, air is holding the air is having the 50% relative humidity. So omega comes out to be 0.00727. So what we will do here is we will draw one vertical line for 20 degrees Celsius dBT, and along this ordinate we will mark the specific humidity having a value 0.00727 and draw one horizontal line from it. So intersection will give me a point number C. Likewise, we will continue to do that for different dry bulb temperatures. Suppose again we wish to generate one more point which lies on this relative humidity line of 50%. We will choose some other temperature, that is dry bulb temperature of 25 degrees Celsius. So at 25 degrees Celsius, what we shall do, we shall enter into the steam table and look for the saturation pressure. So whatever be the value of the saturation pressure, make half of that, that will be the partial pressure of the water vapor at 25 degrees Celsius having relative humidity 50%. We'll again determine the new value of the partial pressure of the dry air and calculate the omega, that is the specific humidity at 25 degrees Celsius having 50% relative humidity. So that is the process of developing the constant relative humidity lines on the psychrometric chart. Likewise, we will do that. We will continue to generate space, that is relative humidity lines for different values. Now it will be demonstrated how the constant specific volume lines are generated or developed on the psychrometric chart. Let us consider a line corresponding to a specific volume of, say, 0.85 meter cube per kg of dry air as shown in figure 1 here. So this line is passing through the point number A and point number B, and uh, let us consider that this is the specific volume. This is the line for constant specific volume of 0.85 meter cube per kg of dry air. So how this line would be generated? So it is for sure that one point on this constant specific volume line is point number A, where it meets the saturation curve, means its thermodynamic state lie on the saturation curve. So in order to locate this point, the following trial and error procedure is to be followed, because it, it is obvious that one end of this constant specific volume line would fall on the saturation curve, but at what value of dry temperature it meets the saturation curve, that is not known to us. So what we will do next is we will assume some suitable dry bulb temperature at point number A and find the PS equal to PV, because at point number A the air is saturated, so partial pressure of the water vapor is equal to the saturation pressure at point number A. So we will simply assume the temperature at point number A, then find out the PS equal to PV with the help of the steam table, and having determined this PS or PV, we will calculate the partial pressure of the dry air part, and then we will calculate the specific volume and check it again. So in this particular case, an assumed value of 20 degrees Celsius is taken initially, at which the partial pressure of the water vapor, which is equal to the saturation pressure, if you still remember the value, this was 2342 Newton per meter square. So we calculate the partial pressure of dry air with the help of this partial pressure of water vapor as 98983 Newton per meter square. Now, having determined this partial pressure of dry air part, we will simply calculate the specific volume of the dry air part as RA into T divided by PA. So RA is known to us, 287.3. Temperature is given to us. This is 20 degrees Celsius. It has to be in Kelvin, divided by PA. So it comes out to be 0.85 meter cube per kg of dry air. So it checks with the required value, because we wanted to develop a line, we wanted to generate a line for constant specific volume of 0.85 meter cube per kg. So it is for sure that the point number A now, it is now lying on this constant specific volume line of 0.85 meter cube per kg. So since it checks with the required value, if it does not agree with the required value, what we shall do, we will again assume new value of the temperature, that is dry bulb temperature, and accordingly again calculate the PS and PV, will determine the value of PA, and again calculate the value of BA. So till this value of specific volume of dry air part matches with this desired value of the constant specific volume line, we will continue to do that. That is why this process is called as the trial and error procedure. So now to point to plot the point A, we will calculate, because we have determined this VA, omega is calculated with the help of the formula 0.622 PV divided by PA. So that will give us a value of 0.01472 kg of water vapor per kg of dry air. So what we will do now, we will draw one vertical line for dry bulb temperature of 20 degrees Celsius and one horizontal line for 0.01472 kg of water vapor per kg of dry air. So intersection will give us a point number A. So this is definitely one end of the constant specific volume line on the psychrometric chart. Now one more point is required in order to develop a straight line, because with the help of one point we cannot generate a straight line. So one more point is needed. So consider now another point B on this particular line at a DVT of 25 degrees Celsius. Now we have considered here one more point B. Suppose it lies on 25 degrees Celsius DVT, and accordingly we will calculate the partial pressure of the dry air part. So partial pressure of the dry air part is calculated as RA into T divided by VA. Mind it, the specific volume at point number A and point number B are going to be same now. So we will put VA as 0.85 meter cube per kg of dry air here. So PA is calculated as 100,724 Newton per meter square. With the help of this PA, we will determine the value of PV. So PV is calculated by subtracting this PA from the total barometric pressure. So it comes out to be 601 Newton per meter square. So having determined the value of PA and PV, now we will calculate the value of omega corresponding to point number B. So point number B now lies at the intersection of one vertical line drawn from this DBT of 25 degrees Celsius and specific humidity of 0.00597. So we will simply join the point number A and point number B and will extend this line up to the abscissa. So this is going to be the line for constant specific volume on psychrometric chart. Likewise, the lines for other constant specific volume values would be generated on this psychrometric chart. Now we shall see how the lines of constant thermodynamic wet bulb temperatures are generated on psychrometric chart. Uh, in order to understand this, you need to again recollect the discussion on the adiabatic saturation that we had in the previous lectures. There is a very large container which is perfectly insulated from all around, containing a very large quantity of water. So it basically provides a large sheet of water, unsaturated moist air at a dry bulb temperature of T, having that is specific enthalpy of moist air as H, and having specific humidity of omega. It enters into that adiabatic container, and we assume that this bed of the water is very large. So ultimately what happens when the air comes out of this adiabatic saturator, it is perfectly saturated at the temperature of the water itself. So its temperature drops from the initial dry bulb temperature T to the temperature of the water T star. Specific humidity level definitely goes up because certain amount of water is ultimately evaporated and get mixed with the air. So its partial pressure of water vapor continues to increase, and its specific humidity also increases from omega to omega star. So omega star is the specific humidity corresponding to the saturation of the air at temperature of the water T star. Specific enthalpy of the moist air will also increase because the partial pressure of the water vapor has gone up, moisture has been added into this air. So enthalpy would change from H to H star. So ultimately, because of the evaporation of the water and the that is mixing of the same with the moist air will result into what? A slight decrease in the level of the water contained in this container. So in order to maintain the water at constant level, what we need is we need to provide the makeup water from the outside, from the external source. So how much makeup water is required to be supplied into that container? So that will simply be the difference of what quantity of water has been evaporated and ultimately got mixed with the unsaturated air, making it saturated at the exit. So this is going to be omega star, that is the final specific humidity level at the exit of this, which is equal to the saturated specific humidity minus the initial specific humidity of the unsaturated moist air. So omega star minus omega, this much quantity of water per kg of the dry air is required to be supplied from the outside or from the external source into the adiabatic saturator. So when we plot this process of adiabatic saturation on the TS chart, we notice that the initial state of the moist air, that is having dry bulb temperature of T, specific enthalpy of H, and specific humidity of omega, the partial pressure of the water vapor in this given sample of the unsaturated moist air, it is at point number A. So because of the continuous evaporation of the water and that is continuous rise in the moisture level of this unsaturated moist air, what will happen? The partial pressure of the water vapor will continue to increase, but the temperature of the air will continuously fall. So ultimately it moves along this adiabatic saturation process, and eventually when the air comes out of this adiabatic saturator, it is at point number C. So air is now holding the maximum amount of moisture at the temperature of the water itself. So its temperature has dropped from this point number A to point number C. So there is a decrease in temperature from this dry bulb temperature to temperature of adiabatic saturation. Partial pressure of the water vapor has increased from this initial partial pressure of water vapor PV to saturation pressure at point number C. Now, what we are going to do is we are going to suppose generate a line for constant thermodynamic wet bulb temperature of 20 degrees Celsius. So when we go for making the energy balance of this adiabatic saturator, we come across this particular energy balance equation. So H is the enthalpy of incoming air plus omega star minus omega into HF star. This is also the energy that is moving in. So plus omega star minus omega into HF star is going to be equal to what? That is the saturated enthalpy at point number, that is at the exit of this container H star. So H plus omega star minus omega into HF star is going to be equal to H star. So this is the simple energy balance that we have, and let us call it as equation number 1. If we rearrange the terms of this equation number 1, what we get is we get H minus omega into HF star equal to H star minus omega star into HF star. So if we just insert the values into this equation, we find that this difference is going to be a constant term. Now in figure 3 at point number A, the dry bulb temperature is 20 degrees Celsius. So point number A, since it lies on the saturation curve, it also carries a thermodynamic wet bulb temperature of 20 degrees Celsius, because when the air is saturated, all the three temperatures, dry bulb temperature, wet bulb temperature and dew point temperature, they become equal. So the point number A at 20 degrees Celsius dBT also has a WBT of 20 degrees Celsius. For any other point on the 20 degrees Celsius constant WBT line, we must have H minus omega star omega into HF star equal to H star minus omega star HF star. So this value, the difference of this H and omega HF star, is denoted by a symbol omega for unsaturated moist air, and when the air has become saturated, it is going to be a difference of H star and omega star HF star, and let us call it as omega star. So what we observe for this particular process is that this sigma heat function does not change. When we move along a line of constant thermodynamic wet bulb temperature, the sigma heat function is constant along the WBT line. So all states on this constant WBT, that is constant WBT line or constant sigma heat function line, will have a combination of H and omega, which will satisfy the equation number 2. Now for point A, what we do is we determine the value of omega star. If you still remember the previous slides, at 20 degrees Celsius we had omega as 0.01472 kg of water vapor per kg of dry air. So with the help of that, we calculate H star. Mind it, the H star is nothing but the enthalpy of this saturated air corresponding to point number C. So it is again going to be equal to what? The enthalpy, specific enthalpy of the dry air part at the temperature T star. So it is going to be CPA into T star plus 1.88 is nothing but the CPV. So this is going to be the enthalpy of the water vapor contained. So expression for this H star gives us a value of omega star. We have already determined 0.01472. Temperature T star is known to us. This is 20 degrees Celsius. Inserting all these values in the expression gives us H star equal to 57.45 kilojoules per kg of dry air. Now HF star is nothing but the enthalpy of saturated fluid that we can directly have from the steam table. So at 20 degrees Celsius, HF value is 83.9 kilojoules per kg. Now we determine the sigma heat function corresponding to the saturation state. So it is going to be H star minus omega star into HF star. So we again insert the value. H star is 57.45, omega star is we already know its value 0.01472, and HF star is 83.9. So this sigma star comes out to be 56.21 kilojoules per kg of dry air. Now for point B, suppose the point number B lies on this constant WBT line but at some different value of the dry bulb temperature. Say the dry bulb temperature at the point number B is 30 degrees Celsius. So the parameter that does not change is the sigma heat function. Sigma heat function at A and sigma heat function at B, it does not change. So sigma heat function at point number B is going to be H minus omega into HF star. Since definitely at point number B the air is not saturated, it is simply a moist air, so it is going to be H minus omega into HF star, but H now it is to be calculated at 30 degrees Celsius. Omega is now again required to be calculated at 30 degrees Celsius. So what we do is we insert the values of this enthalpy of moist air. It is going to be 1.005 plus 1.88 omega. Omega is not known to us. Into dry bulb temperature is 30 degrees Celsius. Plus 2501 is the enthalpy of evaporation at 0 degrees Celsius into omega minus 83.9 HF HF star is known to us into omega. So the left hand side of this equation basically contains one unknown parameter, that is the specific humidity at 30 degrees Celsius, but the right hand side of this is known to us because sigma is equal to sigma star, and sigma star we have already calculated as 56.21. So sigma star is corresponding to point number A, sigma is now corresponding to point number B. So the sigma heat function does not change as we move along this constant WBT line. So equating this whole thing to 56.21 gives us a value of specific humidity as 0.01072 kilojoules per kg of dry air. So what we will do next is we will draw one vertical line for constant constant dry bulb temperature of 30 degrees Celsius and one horizontal line representing omega of 0.01072. So intersection will give us a point number B. So we will simply join the point number A with point number B and extend this line. We will also we can also determine the value of, that is different values of omega at different dry bulb temperatures by following the same procedure. Now we shall learn how the constant enthalpy lines are developed on the cyclomatic chart. If you guys still remember this energy balance for the adiabatic saturation process, H plus omega star minus omega into HF star is going to be equal to H star. It may be observed from the preceding calculations that the difference of the enthalpies at the saturation point A and another point B on the constant WBT line is very small. The difference denoted by the symbol capital D is called enthalpy deviation, and it is given as H minus H star. Obviously, the enthalpy of the saturated air at point number A is denoted by H star, and the enthalpy of unsaturated moist air at point number B is denoted by H. So H minus H star, so with the help of this particular equation, H minus H star is nothing but this much, omega star minus omega into HF star. So in spite of the small enthalpy deviation, separate lines of constant wet bulb temperature and constant enthalpy can be shown on the cyclomatic chart if it is made sufficiently large. Many cyclomatic charts allow this, follow this practice. Another method suggested by Parmentier and Weil uses the constant WBT line and also shows constant enthalpy deviation lines as shown in figure 1. The enthalpy deviation at B is equal to the enthalpy for state B was calculated as 57.11. Enthalpy of the saturated air at point number A was calculated as 57.45. So this difference is going to be minus 0.34. So what we do is we move along this constant WBT line and separate enthalpy deviation lines are plotted. So whatever be the value, because ultimately what happens, the enthalpy scale given on this cyclomatic chart, it simply gives us the value of the enthalpies at saturation state, that is only the H star values are given to us. So in order to determine the enthalpy at any other point, like at point number B, we move along this constant thermodynamic wet bulb temperature line and look at the enthalpy deviation. So we will simply add this enthalpy deviation to the value of enthalpy at point number A. So value of the enthalpy at point number A is 57.45 plus minus 0.34 will give us a value of 57.11 kilojoules per kg of dry air at point number B. So enthalpy of this unsaturated moist air can be calculated using this enthalpy deviation lines, H equal to H star plus D.